Up until now, we've been learning about how to locate the image produced by a mirror with ray diagrams. We're now going to learn about the equations and the math involved with locating an image and determining about how tall the image is and some other properties of the image. We'll have three main equations that will help us do so. The first equation is 1 over the focal length is 1 over the object distance plus 1 over the image distance. The second equation says that the magnification, that's a term that tells us about how much bigger or how much smaller the image is when compared to the object, is equal to the image height, hi, divided by the object height, ho. Our third and final equation tells us that magnification is equal to negative di over do. The negative image distance divided by the object distance. Before we can jump into using these three equations, we need to know some things about sign conventions. In other words, when do we use positive signs and when do we use negative signs? The first sign convention is that any time your distance is measured behind the mirror, we'll use a negative sign for that distance. Well, it doesn't make sense to ever put your object behind the mirror. You'll never get an image from that. But your image distance can be negative, because sometimes we get an image that appears behind the mirror. That image is a virtual image. Virtual images are always located behind the mirror and thus always have a negative image distance. Also, with convex mirrors, the focal length is always negative because the focal point is located behind the mirror. Magnification is negative when the image and the object have opposite orientations. In other words, when one is upright and the other is inverted. Image height is negative when it is inverted. Object height is typically positive. Finally, the last note to make before we jump into using these equations is that when the absolute value of magnification is greater than 1, it means that your image is larger than the object. It's magnified, we typically say. If the absolute value of m is less than 1, then the image is smaller than the object. Let's go ahead and try this out with our first problem. This is a continuation of a problem that we have already tried where we drew the ray diagram. We now get to use these numbers and the equations we've learned to find exactly where the image is located. In this one, we're given the object position and the focal length. And so we'll use the equation 1 over focal length is 1 over object distance plus 1 over image distance. I'll go ahead and just plug in numbers rather than solving for the variable on this one. It tells me the focal length is 16 centimeters, so 1 over 16 centimeters. It tells me that my object is located 36 centimeters in front of the mirror, and I want to find where the image is located. Now, before you plug any numbers into your calculator, you should have an idea of what number you'll come up with. That's due to the fact that we should know those 6 scenarios. If my focal length is 16 centimeters, that means my radius is 32 centimeters, because radius is always twice the focal length. So my object is located outside of C, which means my image should be between C and F. That corresponds to the second scenario. C is 32 centimeters away from the mirror. F is 16 centimeters away from the mirror. So when I solve for the image distance, di, I should get a number between 16 and 32. And I do. The number I get is 28.8 centimeters. I know that number makes sense because it follows the second scenario. Therefore, I can box that answer and know that I'm finished with the problem. A word of advice is to always check this against the scenarios. It helps just in case you end up making some goofy math errors along the way. Moving on to the next problem. Here, a 3 centimeter tall object is 20 centimeters from a 16 centimeter radius concave mirror. We are trying to find the image position and the image height. The first thing we'll do is find the image position. Using 1 over f is 1 over dO plus 1 over di. Now, you may have noticed in the last problem, as well as in this problem, that we're not going to convert units. You're allowed to keep the units as they are, as long as all of your units match. If I had a mix of centimeters and millimeters, I'd have to find a common unit. But because they all match, I don't have to worry about converting, which is kind of nice. Looking at the information I'm given, I'm told where the object is located. That's dO, which is 20 centimeters. I'm looking for the image position. That's di. But this 16 centimeters that I'm given, that's not the focal length, that's the radius. But remember, the focal length is half of the radius. Or you could say the radius is twice the focal length. So if the radius is 16 centimeters, my focal length is 8 centimeters. I can use this equation now to solve for the image position. Again, before I do any math, before I use my calculator at all, I can have an idea of what range my answer should be in. I know that the focal length is 8 centimeters, the radius is 16 centimeters, and my object is located at 20 centimeters. Once again, that follows that second scenario. My image distance should be somewhere between 8 and 16. And again, it is. 13.33 centimeters is my image distance. We're also asked to find the image height. We only have one equation that includes image height. That's the equation that says magnification is image height divided by object height. Now, I know from that second scenario that my image is inverted. So my image height should be negative. I also know that my image should be smaller than my object. My object height is 3 centimeters. So I should be getting a number that is less than 3 centimeters and is negative. Based on the information I'm given in the problem, I do not yet know magnification. But I do know magnification is negative di over dO. Because magnification is equal to both of these equations, the equations are equal to each other. Image height is what I'm looking for, so I will multiply both sides of the equation by object height. So that I find image height is negative image distance times object height divided by object distance. Then I get to plug some numbers in. We already solved for image distance. We found that it was 13.33 centimeters. The object is 3 centimeters tall, and the object is located at 20 centimeters. When I plug all this into my calculator, I get negative 2 centimeters as my image height. Now remember, I said my image height should be negative and should be smaller than the object. And sure enough, it is. This has shown us a couple of examples using concave mirrors. Let's look at an example with a convex mirror. In this example, An object is located 20 centimeters in front of a convex mirror with a 15 centimeter focal length. Find the image position. Just as we did in the first example on this video, we'll use the equation 1 over focal length is 1 over object distance plus 1 over image distance. The thing that's different with this problem, and the fact that it's a convex mirror, means I need to put in a negative focal length. If I forget that negative sign, I will get an incorrect answer. Again, before I do any math or plug anything into my calculator, I'm going to pause and think about the properties of convex mirrors this time. I know convex mirrors always have a negative focal length. I also know that they always produce a virtual image. Virtual images are always located behind the mirror. Therefore, they should have a negative image distance. So when I plug numbers into my calculator, I'm expecting a negative image distance. And sure enough, that's what I get. I find the image distance to be negative 8.57 centimeters. With this one, we don't know anything about should it be between this number and the other number, because we don't have 6 scenarios for convex mirrors. But we do know that it should be negative, and this is a reasonable answer. Therefore, it is our final answer. We'll do more practice with these equations in class. So make sure that you bring your textbook and notes to class with you.